All right. Ethernet provider bridge. So now the Ethernet is getting into the business, the IEEE actually is getting into the business of somehow fixing Ethernet so that the carriers can use it. First came MPLS, they fixed IP, they fixed MPLS so that carriers started buying MPLS rather than SONET, which was their favorite. Right? And then the Ethernet guys said, why do we need this MPLS? Why do we need IP? We can just do everything on the Ethernet itself. So they decided to design many things. Actually, the OEM was not the first thing they designed. They designed PB first. So let's see what is PB. PB is short form for provider bridge. Provider is carrier bridge. So basically, let's assume that there is a carrier and you have a building here and a building there and a building here and a building there and you want to connect. We saw this picture before. And so we have a carrier edge device, sorry, not carrier, customer edge device, CE, and this is provider edge device, and so on and so forth. The main problem, first problem that you run in is that if you have multiple customers, they are going to use the same VLAN numbers. You know, I may have VLAN number 100, you may have the VLAN number 100. Now when we try to route the packets, we don't know who is 100 we have. Why the difference? So think Uni is the interface, CE is a device. In between, if you draw a line there, that would be Uni. CE is a switch or a device or a router or something. PE is a switch or a device or a router or something. Okay? The connecting point between the two, there is an interface. So Uni is an interface. I for interface. This is E is for the edge and the device. Interface is not a device. Interface is basically, if it is a device, then somebody has to own it. Interface is, okay, so let me explain an interface. Let's say I write a program, okay, which you are going to use. You will define an API. That is an interface. But it's not a program. I write a program, you write a program, and there is an API in between. Right? So that is, it's just, okay, so interface, let me give you another example of interface. Interface that we use every day is Ethernet interface. When you take an Ethernet cable, and there are 8 wires in it, there is an interface defined which says the first wire should be this, second wire should be this, third wire should be this, the signal level should not be more than 200 volt, otherwise we will burn up, things like that. That is an interface, it's not a device. It's just a piece of paper which tells you what should be followed. Alright? And the interface is basically, you know, those wires. Similarly, when you have a phone company, I already told you that the phone company has this RJ11 port outside, that's an interface. RJ11 belongs to them, but then the wires have a meaning. Okay, so, okay, hold on. If I said that, I probably simplified things a bit. Interface is a line. Now I'm simplifying it, I know. But it's a plane, you know, I mean, it could be a line, it could be a plane, or whatever it is, dividing between the two. And then everything that crosses that line or a plane has some meaning defined. It's like an API. Alright, so now we understand what is CE and PE. Now second thing I will tell you what. There are two kinds of networking people. I have a good cartoon which is not here right now. One is called bell heads and one is called net heads. Bell heads work for the AT&T and for Bell Labs. They only think in terms of unis and things like that, right? And the net heads are people like us who work for the universities and teach data networking and actually work for Cisco and other companies that do data networking. We don't think in terms of interfaces. Even IEEE, you go ahead, I mean, now you'll hard to find, you know, words unis and things like that. We still use these CEPs, blah, blah, blah. So there is that difference too. ITU uses uni all the time and they have, you know, it's like OAM, you know, now we are learning OAM. So the net heads are learning the bell. So what is happening? The two worlds are mixing now. So the bell heads are learning about the net and the net heads are learning about the bell. Okay. So that's the thing you'll find that I may not be using a uni word here, but it has, you know, this is what the IEEE does too. All right. So now we need to, let's back to the problem. The problem was that there are too many people using the same VLAN number, so we cannot distinguish with them. So there is a new standard called AD, 802.1 AD, which was done in 2005, and it's called provider bridge, and it's also called Q in Q, and that is a good name. Q in Q means that we have a VLAN inside a VLAN. Q is VLAN, right? 802.1 Q is a VLAN standard. So Q in Q, this Q is not QUE, Q is VLAN. Q in Q is basically what happens is you put another VLAN on the front of it. So there is a customer VID, which is customer VLAN label or whatever that is, and this is the service VLAN or something. So instead of calling provider, they call it here service for whatever reason. So the service provider's VLAN. Service provider puts its own VLAN, and let's say it calls this one VLAN 1 and this one is VLAN 2. Now inside this VLAN are all the VLANs that are coming from customer B. All the packets actually that are coming from customer B. That could be some unmarked packets, that could be some tagged packets, that could be some other packets. Alright? And similarly this one has another VLAN. So this solves several problems. Not only it solves the problem of keeping the customers separate, it also solves the problem of one customer's unknown packets going to the other customer's unknown packets. You see, unknown packets, we don't know who they belong to, and therefore we broadcast them. Right? And if I send lots of unknowns, I could have a bug in my computer and generate lots of unknowns, then I could affect you because you're using the same carrier. With this, everybody is kept separate on a separate VLAN inside the carrier. So when the packets enter this carrier right here, a new VLAN tag is added. When they get out, that VLAN tag is removed. Okay? So now you have two VLANs. One is the service provider's VLAN, which is called SVID. One is called carrier's VLAN, which is called CVID. And the numbers of the protocol type are 8100 and 88484. Now check in your handout, this number should be there. So this is called Q in Q, because we have two 802.1 Q headers. Alright, now you can have 4,000, you can have 4,024 VLANs. Service provider can have 4,024, and each customer can have 4,024. The total number of VLANs can be 4,000 times 4,000, which is 16 million. So can you do it 3 times? Yes, and I can do it. And they did it. But right now let's stay with 2. Now, that tag VLAN, service VLAN ID has basically is 12 bits, and then there are 4 bits in front of it, priority and CFI. Now these priority and CFI are not the customer priority or customer CFI. These are service providers priority and service. So you are a customer Bank of America and this is a customer Raj Jain. So AT&T will assign different priorities to the traffic. Right? And that is the priorities put here in this tag. In the outer tag, the priority is the priority for the service provider, right? Which could be different from the customer's own priority. Depending upon how much you pay, you get higher priority. The whole thing is called S tag. So the tag means the whole thing, and VLAN ID is just part of it. 12 bits are called VLAN ID, and this whole thing is called S tag. It turns out this whole thing actually 16-bit plus 16-bit, oftentimes we prefer to just indicate separately. So this is 16 bits plus 16-bit. Type is shown separately so that you can figure out what is next. So this is 16 bits right there. Out of that 16-bit, and we call it SVID, out of that 16-bit, 12 bits are really the VLAN ID, and then there are 4 bits which are priority and the CFI. So there was 2 kinds of addresses. First was Ethernet address, the IEEE 802.3 addresses, and there were 5 addresses, token ring addresses, and they were written differently. So they had canonical format indicator to indicate whether the address is in this format or that format. We no longer have token ring, and therefore all the addresses are canonical. So we use it for DEI, which is drop eligibility indicator. Right? So same thing here. That would be drop eligibility indicator. This is your priority, this is your drop eligibility indicator. And the priority could be strict priority or could be AF, assured forwarding. This is why I taught you differentiated services. So assured forwarding kind of thing you could use. And here actually there is a mismatch because they talk about 6 AF. So whoever designed it didn't know that the AF is only 4. So it doesn't really matter. All it means is there are 6 classes and they're not related, right? There's no reason that AF1 or AF6 gets any better service than AF3 or AF4. They're just different queues, right? So the number of classes is unimportant, but they call it AF. All right. So we just finished a whole set of standards called provider bridge. And what provider bridge now allows you is that it allows you to go over one carrier. As soon as they started deploying this, they found out there's another problem. That you really don't go over one carrier, you need to go over multiple carriers, and when you go over multiple carriers, you run into another problem. So let's say you are here subscriber, you go over a provider, and then they go over a backbone, which is somebody else. So this could be tier 3, this could be tier 2, somebody else. Now that somebody else has to remember everybody's addresses, because remember the forwarding is still by the source and destination addresses, and it has to be learned. So you have to find out where the packets are coming from and remember all that, and then when some packets comes, you know where to send them. Alright? So if this provider is serving 10,000 customers, 10,000, 10,000, 10,000 here, this is serving 40,000 customers, each of them have 1,000 addresses. This is guy is going crazy, trying to remember all those addresses and learning them and unlearning them, right? So there were just too many Macs to learn and unlearn, and so they said, okay, all right, we will do all this job in big boxes which we'll put at the edge, but in the core we don't need to remember any of this. So they designed another standard which takes care of this large number of MAC addresses, and that is called MAC in MAC. So MAC in MAC, the name is on the next slide. Basically this is 802.1 AS 2008, 5 years ago. And so what they did was they said we will take the packet that comes in, right here we will decide where it is going, and rather than let everybody inside trying to figure that out, we will put the destination of the exit bridge. We will put the address of the exit bridge. That way the core can be simple and core can go fast. So here is the edge, here is the core, and the edge bridge still has to remember all the addresses. So when it sees a packet, it remembers it came from here, and when it sees a packet coming from here, it sees it coming from here, and then they exchange and they know that when packet is going to that address, it has to be sent to that bridge, and so they keep complete address list here in the edge. Those are big switches. But when the packet is sent inside, they put another address in front of it. So they have a BDA, BSA, and that is the bridge or backbone actually. Backbone destination address, backbone source address. So the core addresses only have to learn BDA and BSA. They have to know when the packet is going to BDA, how to send it. It's a smaller subset, very small subset actually. Backbone destination addresses. Only the backbone core only needs to learn about the backbone, the carrier's its own switches addresses and ports addresses, device addresses, and not the whole world. Now when we are adding the addresses, we might as well add a VID. So this is your third queue we were talking about. So this is the backbone VLAN address. Now when we are doing VLAN ID, we might as well put a fourth one, which we call service ID. What is service ID? So basically, the VLANs are set up by the carrier so that it can delimit its broadcasts. And just like we had pseudo wires inside MPLS, similarly, you could have pseudo wires. We won't call them pseudo wires because that word is taken up by IP. We call them service. So we can have service IDs, which are thin wires going through those big VLANs, and each thin wire serves a customer or serves a particular kind of traffic and serves a particular kind of VLAN, and we will define that more precisely in a minute. But every service has a packet which goes through a particular VLAN. And each VLAN could have hundreds of such service wires. And we won't call them wire yet because there is no really a wire. The packets are just connectionless. Wire means connection, by the way, in some sense. So anyway, service. So there are now 4 kinds of things. Now this is really not a queue, so I wouldn't call it queue because this is a service ID which is 32-bit long. Whereas SV ID was 16-bit long. So we have a lot more bits here to indicate a service, and therefore the different type here. This is not a type which says that this is a LAN and this is a VLAN. This says this is a service. So this type indicates that this is a service and this is a service ID. Alright, so let's just revise the whole thing. So this is what is this address? Backbone destination address. This is the backbone source address. This is the type, which is actually the same as here. So it doesn't really matter whether you have one more there or not. All we know is that this is simply a VLAN. So we look at the VLAN and then we forward, because all the core bridges forward based upon 2 things. They forward based upon the destination address and the VLAN. 60 bits. The same destination address on a different VLANs will take a different path. The same different destination address on the same VLAN, may take a different path. So we need both the destination address and the VLAN to find out which port I should send it out. So those 3 things are used, VLAN ID and the destination address, 2 things are used to forward the packet. This is not used by the core at all. The core doesn't even look at the service or anything like that. And this is a standard Ethernet definition now, whether this is PBB bridge or whether it is a PB bridge or whether it is a customer bridge. Everybody does this. They just look at the destination address and the VLAN ID and they send the packet. That's the standard definition, standard thing. So this is nothing new. Now we have the service IDs. Service IDs, basically what it does is it allows you to somehow have in one VLAN many things that you can distinguish later on. And so it's the same concept that we had before. So what is a service? A service could be all frames coming on a specific port. Everybody coming through that door is one service, because that door goes to Bank of America. Or everybody coming on that door with a service VLAN of AT&T. So anybody who is coming through that door and came from AT&T, they have the service VLAN of AT&T. Remember that PB? That was called SVID. So if your SVID is 5, you go on this service. Your service number is something. Or anybody coming from a specific port with a specific service LAN with a specific customer VLAN. Or we could go one more level inside the packet and see, okay, you have this service VLAN and you are coming from that customer of that carrier, you go on this wire. Okay, so we could go 3 levels deep and define a service. Here's an example. So if anybody who is coming on port 1 goes to SID1, and then anybody who comes on port 2 with VLAN 10, SVLAN 10 gets the service 20. Anybody who comes on port 2 but SVLAN 20 gets the service 33. Anybody who comes on port 2 with service VLAN 30 and the customer VLAN of 100 goes to port 401. Obviously, they could not be that you could put something that doesn't make sense. For example, if I put a 20 here, that doesn't make sense, because they would have gone to 33 and they would not even come to this line. Right? So here, the way I have prepared this table is so that these are all exclusive. So anyway, service 401, service 5, and then there is another table that the carrier prepares, which says that anybody going on service 1 should go on VLAN 1, anybody going on service 2 should go to VLAN 3, anybody going on 401 should go to VLAN 4, 502 should also go through VLAN 4, which I have shown by a figure here. So the traffic on port 2 is divided 3 ways. One of them goes to VLAN 4. Traffic coming on port 3 goes to VLAN 4 too. You can see 2 of the services are using the same VLAN. Alright, so now you see the need for a service. Basically, and the second thing is that there could be many services, because services could go all the way to the customers. So how many customers could we have? If you are a backbone, so you already have so many carrier customers of yours, and each of those carrier customers have their customers. So you could have lots of services here, and therefore services need 24 bits. Services need 24 bits, and so those 32 bit that you saw instead of 16 bit, now we extended it to 32 bit. Out of that, 24 bits are service ID, and then we have 8 bits left, which are defined as follows. First 3 bits are priority, and 1 bit is DI. This is how it was in the case of VLANs 2. We had 3 bits of priority and 1 bit of CFI or DEI. Then they added these more bits, and they didn't know what to do with these 3 bits, so they are reserved. But there is 1 bit which says use customer address. Okay, and this is generally used only in CFM. So when you want to do connectivity fault management, then you want to check how far your trace route is going, or how far is your ping is going. You can use that bit set, and it will go to that part, customer address as well. And then you have 24 bit of SID. Technically, this whole thing is called S tag, and this is called I tag, and it includes the customer destination address and the customer source address. So if you go back to the previous picture here, you see right next to the ISID is the customer destination address and the service source address. This whole thing is called I tag, although none of it is used by the core, but in some of the OAM you might need that. Alright, so now let's see a pictorial one more time. So a service, multiple services could go through a VLAN. So this is a VLAN. Now notice VLANs don't have to be point to point. VLANs are virtual LANs. Just like a LAN, they could be point to multi-point. And so there it is. This is a VLAN. This whole thing is one VLAN. In that we have 2 services going. One service is this orange or whatever color that is service, and that is SIDA. And then there is a blue service which is point to multi-point, and it's going that way. This is another VLAN, and it has 2 services going, both point to point. So you see the services themselves are like virtual private virtual LANs, and they could be inside another virtual LAN, which are the service providers virtual LANs. So this is backbone virtual LAN. So this is BVLAN, means backbone virtual LAN, and this is the PBB core bridge. This is the PBB core bridge, and it doesn't need to look at the service ID. It doesn't look at the service ID. What it does is it looks at the VLAN ID. It looks at its own VLAN ID and the source and destination, and it sends the packet. Service is not looked at inside. So what we have learned so far is what we call PBB, provider backbone bridging. So first was PB, provider bridging. Then was PBB, provider backbone bridging. Alright, Mac and Mac.